Welcome to the first example of converting a double integral in rectangular form to polar form. In the intro video, we discussed how it was important to be familiar with the formulas used to convert rectangular equations to polar equations, as we see here. So if you don't already have those in your notes, you may want to copy those down. We also talked about how if f of xy is a continuous function on a polar region, defined as we see here in terms of r and theta, then we can convert this double integral in rectangular form into a double integral in polar form. And if the region of integration is easily defined in terms of polar coordinates, it's often easier to integrate in polar form. But there are a couple important things to remember when doing this conversion. First, our function f of xy had to be converted into an equation in polar form, or a function in terms of r and theta. And we did that by replacing x with r cosine theta and y with r sine theta. And then in rectangular form, dA was equal to dx dy or dy dx based upon the order of integration. But now we're going to replace differential a with an extra factor of r dr d theta. And we talked about in the introductory video where this extra factor of r came from. It actually comes from the arc length formula. So if you want to review that, you may want to take a look at that video first. In this video, we're going to focus on converting this double integral in rectangular form to polar form and then integrating it. So the first thing we want to do is determine our region of integration. Taking a look at this integral here, because we're integrating with respect to y first, this tells us that y is going to be greater than or equal to 0 and less than or equal to the square root of 9 minus x squared. Let's go ahead and write that down. Again, y has to be greater than or equal to 0, and y has to be less than or equal to the square root of 9 minus x squared. And we also know that x must be greater than or equal to 0 and less than or equal to 3. So x is greater than or equal to 0 and x is less than or equal to 3. Let's see if we can graph this region. So y is positive, meaning it's only going to be in the first and second quadrant. And also y is less than or equal to the square root of 9 minus x squared. Let's square both sides of this. We would have y squared less than or equal to 9 minus x squared. And if we add x squared to both sides, we should recognize this as a circle with a radius of 3. So we're going to graph half a circle because we know that y has to be positive. It's going to pass through these 3 points. And because y has to be greater than or equal to 0, we know we're above the x-axis. And now we also know that x has to be greater than or equal to 0. Well, here's where x is equal to 0. So we have to be to the right of this line. And then x is also less than 3. So that's enough information to tell us our region of integration. It'll be this region here. Our next step is going to be to rewrite f of xy in terms of r and theta. Well, we know x squared plus y squared would be equal to r squared. So f of r theta would be the square root of, this would be r squared to the third. Well, this would be r to the sixth, and the square root of r to the sixth would be r to the third. So let's see if we can set up our double integral in polar form. So f of r theta will be r cubed. Now don't forget we have an extra factor of r and then dr d theta. And the last step here is to see if we can determine what our limits of integration should be. So because we're integrating with respect to r first, and this is our region of integration, and because we're integrating with respect to r first, meaning the radius, we know the radius of this circle is equal to 3, so our limits of integration with respect to r are going to be from 0 to 3. And then for our limits of integration with respect to theta, because we're only dealing with the first quadrant, our angle theta would be from here to here, which would be from 0 to pi over 2. So now we just need to multiply this and then start integrating. So we've got r to the fourth dr d theta. So we're going to have r to the fifth over 5 Let's go ahead and continue this on the next slide. So we're going to have 3 to the 5th over 5 minus 0. This will be 243 fifths. This will be 243 all over 5 theta evaluated at 0 and pi over 2. So if 243 divided by 5, we'll have times pi over 2 minus 0. It'll just give us 243 divided by 5 times pi over 2. 243 over 10 pi. That'll do it for this first example. We'll take a look at another one in the next video.